Our next speaker is Jackson Fliss from University of Cambridge, who'll talk about minimal areas from entangled matrices.
Okay, yes, thank you. And thank you everyone for being here. I'm very excited to be here and to tell you about this work, which really has at its heart a question that drives the if from qubit community, which is how does geometry emerge from information? And of course, we've heard a lot that this really has roots in Bekenstein-Hawking, who told us that black holes are thermodynamic, and they have an entropy that scales like the horizon area. Of course, this question is more foundational than just black holes, and sort of the centerpiece of this is in the ADS-CFT correspondence with the Ryu-Takayama formula, which tells us that a microscopic entanglement entropy, namely the entanglement entropy of a region in a CFT, is given by some geometric quantity in the bulk. It's given by an area of a minimal surface that extends from this region into the bulk. And I think what's a very interesting fact about this formula is that this surface is not determined a priori, or at least in any obvious way from the CFT, but it's really picked out dynamically by bulk effective field theory, e.g. using a semi-classical gravitational path integral, a la Lukowitz and Malacena. And so I would like to look underneath the hood of this mechanism a little bit. So I think to have a proper understanding of Ryu-Takayama, we should really account for several features of this formula. The first is this area as state counting. It'd be nice to have sort of the same level of rigor that we have for black hole horizon microstate counting. And thank you, Samir, for the very inspiring review on this morning. I would also like to have an understanding of the appearance of this inverse coupling as opposed to, say, a UV cutoff that we are often seeing in entanglement entropies in quantum field theory. And of course, this stems from the fact that we're really counting a finite number of degrees of freedom in this entropy, but it's reorganized in a way that tells us something about the bulk effective field theory. Somehow all these degrees of freedom are organized into some bulk effective field theory, and that's why it appears as a coupling. And lastly, and importantly, I would like to understand the appearance of this minimization problem, why it picks out a minimal area. And of course, if we think about this, this has something to do with diffeomorphism invariance, right? We can't pick some fixed fiducial surface. We have to pick a surface that sort of minimizes things. But this is subject to some gauge invariant condition. And here in ADS-CFT, of course, the gauge invariant condition is that we fix a boundary region of the CFT. So in this talk, I am going to try to explain how these features can arise in certain theories of matrix quantum mechanics. And since this is a strings conference, I should also mention that, of course, matrix quantum mechanics has a rich history in string theory. And in particular, there's a rich history of finding emergent spaces in the quantum mechanics of large N matrices. The models I'll be thinking about all have a very similar structure that can be arrived at from dimensionally reducing super Yang-Mills. They have some collection of n by n matrices they'll call X. The Lagrangian has a kinetic term, and then some potential terms which will usually include a commutator square. And we can really think that these models describe the dynamics of emergent D-brane world volumes. So if you're not familiar with the story, a very, very quick rundown of how this works is that we can view the eigenvalues of these matrices as the locations of n D0 branes. Now, these matrices don't commute because there might be strings that are attached to the D0 branes and stretch in between them. And these D0 branes and these strings can then coalesce into higher dimensional membranes, a la the Myers blowup. So it's worth pointing out that also these models are not necessarily quantum gravity and not necessarily holographic, yet they're interesting in their own right. Often they are tractable, and also they'll display key features that I want to explore here. So I'm going to try to talk very generally and establish some principles in which we can find this minimal area formula, but it's also useful to have a grounding example in mind. And one such easy example is what's called the fuzzy sphere state. So we might have three different matrices and a potential for these matrices that is minimized when they satisfy an SU2 commutation relation. And so this fuzzy sphere state is one that's sharply peaked on a classical configuration of the matrices, such that they span an n-dimensional irreducible representation of SU2. And as this irrep of SU2, that means if I sum the squares of these matrices up, I get the Casimir, and this is just some fixed number. And so this is the radius of the sphere. But these matrices also don't commute, so it is a non-commutative sphere, and it has a radius that scales like n, which we will take to be very large. Also central to the story is a gauge redundancy, which I'm going to try to explain plays the role of diffeomorphism invariance that we were talking about in the Ryuta-Kainagi context. So in particular, it has a UN gauge redundancy, which acts on the matrices by conjugation. And at large n, this is going to act on the membrane theory as volume-preserving diffeomorphisms. So one way to think about this is that there exists a Moyal map that maps matrix functions to non-commutative functions on the membrane. And underneath this map, the trace over those matrix functions corresponds to an integral over the non-commutative functions. And since this conjugation by UN preserves this trace, that means whatever is acting on the membrane theory is going to preserve this integral for any polynomial function, and so it has to preserve the volume form itself. And so these are volume-preserving diffeomorphisms. And so another way of thinking of what this talk is about defining volume-preserving diffeomorphism invariant entanglement entropies for D-branes. Okay. So let's give a summary of the result, and then I will try to explain how we arrive at the features of this result. So the result is going to be a minimal area formula. So we have an area here, and the minimization problem is over all possible subregions, subject to the condition that the volume of that subregion is fixed. And along the way, we're going to explain, or we're going to account for this area as a state counting. And the way this is going to rise is that this area will be a dimension of some edge modes under which gauge transformations will act at the edge of a system, a given system. We'll explain why there's an inverse coupling there. Of course, since these matrices are finite, the entropy is already going to be finite at large but finite n. So it's regulated by that. But then there's often a effective coupling describing the non-commutative field theory that describes the fluctuations around a fixed classical background. And in particular, for the fuzzy sphere state, the fluctuations are described by a non-commutative Maxwell theory, and we can replace n with this coupling G max. And then lastly, I'm going to describe the appearance of this minimization problem, which, as I said, there are volume-preserving diffeomorphisms that want to move around subregions, and this is going to arise as a saddle point in the average over those volume-preserving diffeomorphisms. Okay, so this is the results that I think I just would very much like for you to take away, but I'm going to now try to explain how we arrive at this result. So to do so, I want to first pick out what I mean by a subsystem, and I'm going to start with initial partition of my matrix elements into an m by m block. So here I have the top left block of this matrix, or of all the matrices. And for instance, in the fuzzy sphere example, we could think about doing this in a basis where X3 is diagonal and ordered. And so what this does is it picks out the top m latitudes of this fuzzy sphere. And so this is actually a fuzzy cap sitting on top of the fuzzy sphere. That's our initial subregion. And to compute this entanglement entropy, we're going to want to embed this into some factorizable Hilbert space, which is usually called an extended Hilbert space. And here it's going to be just spanned by all possible matrix elements. And it's obvious that this is going to factorize into this block and all the other blocks. And therefore, we can just declare this to be the in region and everything else in pink to be the out region. But as is often common and a feature or maybe a bug, I don't know, of these extended Hilbert spaces, is it's not gauge invariant, right? And the gauge symmetries act on these states, and so we have to isolate the physical states here. And here in particular, it's not invariant underneath UN. And the UN acts on states in this extended Hilbert space in sort of two distinct ways. Firstly, there's this subgroup UM cross UN minus M, which only moves things within a given matrix block. And we can think in terms of volume-preserving diffeomorphisms. These are diffeomorphisms that move within a given subregion or the complement, but don't actually change the boundary of the subregion itself. And then there's also the gauge transformations in the quotient, which I'll denote as F, which actually move elements from one block to another. And in terms of our fuzzy sphere, this will be something that, say, wiggles the edge of the subregion, or even may pick out pockets of the subregion and move it to the complement, which I haven't drawn here, and so drastically change the subsystem itself. So we're going to then try to define an entanglement entropy that is invariant underneath this. So I just explained that a partition of matrix entries corresponds to a subregion on the emergent geometry. And this UN that moves the matrix blocks around are like VPDs that mix around the subregions. And so this leads us to the gauge invariant question: what is the entropy of any M by M block on the matrix theory, or on the membrane theory, what is the entropy of any region of fixed volume? Okay, so that is the question we're going to try to answer here. And to do so, we're first going to start with a gauge fixed state in this extended Hilbert space, and then make it gauge invariant. And we make it gauge invariant by just averaging over the orbit of gauge transformations, right? So we just act on it with some element of UN, then we integrate over all UN. And it's going to be useful to sort of glom the UM cross UN minus M into the state itself and pull out the integral over V. And so in particular, this psi V that I've written here is invariant under a UM action, and it's a particular UM action that acts on an M by M block, the M by M block in the basis that has been transformed by V. Okay, so that's why it's labeled by this V here. And this UM action is actually very familiar to us from the story of entanglement and lattice gauge theories. In particular, it is going to maximally entangle things at the edge of our system. In the matrix theory, these will be guys that live at the corners of these matrix blocks. It will maximally entangle the degrees of freedom at the edge with the things at the edge in the complement into irreps of UM. But it's the guys that live in F that have no analog in local gauge theory. And this is because, as I said before, they actually changed the subregion that we are now tracing out. So these are going to be the guys that'll be more difficult to deal with. But first, let's look at the consequences of this UM invariant and argue that it leads to area laws in the entanglement. So as I said, this is a bit more familiar to us from lattice gauge theory, and there we know that the UM invariance leads to reduced density matrices for physical states that break up into representations of UM, and moreover, these are singlets on these representations of UN. So that means that they're maximally entangled edge modes. And so here, there's some probabilities, and these guys are maximally entangled, and D is the dimension of that representation. And what is interesting about states in matrix quantum mechanics that are strongly peaked on classical geometries is that actually if you compute the quantum Casimir, the quantum variance of the UM Casimir in these states, you'll find that there's a dominating irrep. That is an irrep with a probability that's very, very close to 1 and an exponentially large dimension. And so we'd like to know what the dimension of this irrep is. So we can read that off by, say, computing the expectation value of the Casimir itself. And the features that we need to take note of in this Casimir come from the Young diagram of the corresponding representation, which has some rows and has some lengths to each row. And the other very interesting feature of these states in matrix quantum mechanics that are peaked around classical geometries, that in fact, under the Moyal map, each row corresponds to a different connected component of the entangling region. And moreover, each row length is then proportional to the area of that entangling region. And if this intrigues you, I recommend reading this paper by Alex Frankel, who explained this, I think, fairly clearly. But as a result of this, when we compute the log dimension of the dominating representation, we're going to see that it breaks up into sum over row lengths times the log correction, which then underneath the Moyal map means that we get a sum over area laws for each connected component of the entangling surface times a log correction. Okay, so we're going to take this and we're going to stick it into our pocket, and then we are going to now move along and say, how do we now calculate the entanglement entropy of any M by M block? So we're going to now incorporate this quotient F. So I'm going to make an assumption, it's a pretty key assumption, that reduced states of different subregions are are distinguishable, at least to leading order in N. And this means that the reduced density matrix, the full reduced density matrix breaks up into a block integral over all the V's of reduced density matrix for each V. Now, this is a genuine assumption that I'm going to make, but it's an assumption that you can say corroborate in your model of interest. So for instance, you can corroborate it in this fuzzy sphere model by looking at Haar random sampling over these V's and commit yourself that this is true. But this assumption is going to lead to a replica symmetry. So when I take trace rho to the n, I get a single integral over this now quotient, and I have this dominating representation to the 1 minus n power. And this integral has an interesting structure. So it's sharply peaked at a saddle point, and then has this very small one loop width. I've exaggerated actually the width in this plot, and then it also has some typical values that it oscillates about very erratically away from the saddle point. And these oscillations are actually very well approximated by looking at Haar average integrals. And so by using these Haar average integrals, we can actually estimate each one of these terms. And by doing these estimations, we can then establish that there is a dominance of the saddle point. And so we have this trace rho to the n as this integral, and the dominance of the saddle point means we can approximate it by the minimizer of this. So the minimum over all V, the log of the dominating representation at that V. And this is what gives us our entanglement entropy. We have it as a minimal, as a dominating log dimension of a dominating representation over all V. And given the interpretation of V as being VPDs that move subregions around, but they preserve volume, this is a minimum over all possible subregions with a volume fixed, and then the answer is given by the area of that minimizing subregion. And I went ahead and replaced factors of n with this Maxwell coupling, and there's also a log correction. So the physical picture that we can have in mind is that we started with a state that really looked like it could have been just a decoherent sum over all possible subregions with a fixed volume, but somehow at large n, it really wants to glom on to a very particular subregion, namely the one that has a minimal area, which is this cap with some one loop wiggles. Okay, so a brief recap. I've told you a story of how geometry merges from entanglement and matrix quantum mechanics. What fuels this is this notion of gauge invariant entanglement, and the interpretation is volume preserving diffeomorphisms. And then we saw that when this gauge orbit emits a saddle point, this is what leads to minimal area formula. So lots of natural outlooks. One would be to revisit this assumption of replica symmetry, which is of course enough to get the entanglement entropy when we're very close to 1. But replica symmetry breaking effects, just like in ADS-C, CFT, are important for Ringy entropies. Essentially, what we've done is we've pretended that the bulk could be filled in with a conical defect instead of looking at back reactions. So it'd be nice to revisit this. And be also, of course, very interesting to incorporate Lorentz symmetry and supersymmetry, obviously with an eye for the matrix quantum mechanics that are relevant for flat space supergravity, such as BFSS and BMN. Of course, there's also more matrices there, so that's a technical hurdle that we'll also have to get over. And lastly, and more speculatively, but it's always fun to speculate, is towards Ryuta-Kayanagi outside of the normal domains of holography. So I've presented a story where we gauge fixed this RT surface not to some fixed feature or some fixed boundary, but to a more abstract notion of the entanglement question itself, which is namely, what is the volume of a subregion? And this is the thing that anchored our RT surface. So this opens up possibly new technologies for discussing more general notions of RT, gauge invariant entanglements, and quantum gravity. And I imagine there's some sort of sympathy here with maybe some of the technology that's been developed in the quantum reference frame community as well. So it'll be interesting to explore that. With that, of course, thank you for your attention.
Thank you. Questions? Comments?
Thank you for the talk. How should I understand you make correspondence between the fixing volume diffeomorphism with the gauge transformation? That's Like,
Yeah.
because gauge transformation mess up everything seems badly, but
Yes.
diffeomorphism is very smooth.
No. You're making a good point. It's something that I've a little bit swept underneath the rug. Of course, UN, even at angles to infinity, is actually much more violent than volume preserving diffeomorphism. In fact, it eschews the whole diffeo or even connectedness of it, right? There's obviously UN transformations that take a single matrix element and moves it, which is in the geometric side, like taking a unit of Planck area and then moving that. And so, yes, there are many more of these guys in this map. And in fact, this tends to proliferate this integral. So there is actually a notion of coarse graining the diffeomorphisms that we are actually using here, which is a bit technical, but is, in essence, we're looking at the orbit over things that act geometrically on our subregion. So we're actually trying to pick out the actual volume preserving diffeomorphisms on the matrix side.
Considering a subset of the gauge.
Yes, that's right.
Okay, thank you.
More questions? If there's not, let's thank Jackson again.